Okay, this is 9.5, number 47, and this is our series, and again, we'll use the ratio test to check for absolute convergence. So we do have this -2, so we're going to have to take the absolute value of that when we take our ratio. A to the n plus 1 over a sub n, the absolute value, so I'll take the absolute value of -2, I put it in green to kind of highlight that, because we haven't seen that before. So take the absolute value of -2, the n plus 1, n plus 1 plus 1. Remember, every time we see an n, we put an n plus 1. The absolute value of x minus 1 to the n plus 1. All over this, so again, we could just write the ratio like that since it's not a fraction. So this is the a sub n, the absolute value though. Okay? And then we can break this up into n and 1. And we can add these up. So this is n plus 2. And I can break this up into n and 1. Like we've been doing it, so we can see how these cancel. So these will cancel, and those will cancel, so I end up with this limit, and this is, I put the n's together, so n plus 2 over n plus 1. And then the absolute value of 2 is just 2, so I can write this as this, 2 times the absolute value of x minus 1. And then again, this limit goes to 1. Okay, so pretty much like what we've been doing. And that equals L. So this converges absolutely when 2 times the absolute value of x minus 1 is less than 1. So I can divide both sides by 2, so I get less than 1/2, and then this will imply this interval, -1/2 less than x minus 1 less than 1/2, and then I can add 1 to both sides. And this is my interval of absolute convergence so far. Now I want to check the endpoints. See what happens at the endpoints. Here we go. And when I put 1/2 in here, if I got -2 to the n plus 1, and if I put 1/2 minus 1, I end up with this -2 to the n plus 1, and this is a -1/2 to the n. And these are both to the n power, so I can say this is -2 times -1/2 to the n, and that's just going to be 1 to the n, which is just 1. Okay, think about that again. If I put these both to the n, this is going to be -2 times -1/2, which is 1 to the n power, which is just 1. So I end up with this. And you can see how the limit of this term, as n approaches infinity, is not equal to 0, so it diverges by the nth term test. If I put 3/2 in here, again, we'll take a look at this. We get 3/2 minus 1 when I put 3/2 in for the x in the original series. So I have -2 to the n and 1/2 to the n. If I multiply those, because they're both under n, I get -1 to the n. Times n plus 1. And again, if we look at this limit, it's going to oscillate. Either way, it's not going to be equal to infinity. As n approaches infinity, it's because that's not going to be equal to 0. So as n approaches infinity, this limit will not equal 0. So that also diverges by the nth term test. So therefore, my interval of convergence was my interval of absolute convergence. Remember, this is absolute convergence implies convergence, so this is the interval of convergence. It doesn't converge at either of the endpoints. That's also where it converges absolutely. So therefore, there are no values of conditional convergence. Okay? And then 48. It's a little more interesting. Okay, so here's our series. And again, we'll use the ratio test to check for absolute convergence. And this is 4x minus 5 to the 2n plus 1 all over n to the 3/2. So again, I use the limit a to the n plus a sub n plus 1 over a sub n. So we do have a fraction, so we'll just use the reciprocal invert multiply. So we have the absolute value of 4x minus 5, 2, and every time I see an n, I put n plus 1, plus 1. Okay, so 2 times n plus 1 over n plus 1 to the 3/2, and I've got n to the 3/2 all over this, so that's just the reciprocal of my original, but only with the absolute value. And then I'll rewrite this as 4x minus 5 to the 2n. So this is 2n plus 2 plus 1. So I wrote the 2n plus 1 plus 2, so I could cancel part of this. Leave this as stays the same, this stays the same. So now I can cancel these out. Okay? So I can cancel the 2n plus 1, 2n plus 1, so I end up with just, and I put the n's together, n to the 3 halves over n plus 1 to the 3 halves. And then I've got the 4x minus 5, the absolute value, and that's going to be squared, so I don't need the absolute value because that's going to be positive. And that's going to equal, and this limit, again, as n approaches infinity, I basically have 1. So the limit is equal to 1, and I have 4x minus 5 squared equals L. So it converges absolutely for L less than 1, or for x minus 5 squared less than 1. So if I take the square root of both sides, remember, when you take the square root of something squared, that's the same thing as the absolute value. So now when I take the square root of this, this goes back to the absolute value of 4x minus 5, and the square root of 1 is 1. Then I can remove my absolute value and by making that a negative 1 less than 4x minus 5 less than 1. And then I can add 5 to both sides, and then divide both sides by 4, so I get 1 less than x less than 3 halves. So that's my interval of absolute convergence over there. So that's also the interval of convergence because absolute convergence implies convergence. So let's check the endpoints. Now this is something where you can use just a little bit of your intuition or foresight. Normally we just check for regular convergence, and then we have to go back and check for absolute convergence also if it does converge. But when x equals 1, if I put 1 in here, I get 4 times 1 minus 5, which is negative 1, to the 2n up plus 1 over n to the 3 halves. But I know n to the 3 halves, if I know 1 over that, that's a p-series that converges. So I just checked for absolute convergence while I was at it. And that just becomes this, and this converges as a p-series. Okay, by using the p-series test, p equals 3 halves, which is greater than 1. So this converges. Well, if it converges absolutely, it converges. So testing for absolute convergence is a little bit stronger because it covers not only convergence but absolute convergence. It covers both. So I kind of catch 2 birds with 1 stone. So I checked it for absolute convergence, and that converges. So that's going to be part of my interval of convergence and also part of my values for absolute convergence. The same thing when x equals 3 halves. If I put 3 halves in here, okay, 2 goes into 4 twice. 2 times 3 is 6. 6 minus 5 is 1. So I've got 1 to the 2n plus 1. So I take the absolute value of that, which doesn't really change. It's the same thing, but I'm checking for absolute convergence, and I, again, have 1. This is even easier to see that it's 1 over into the 3 halves, and that also converges. Same thing, p-series, p equal to 3 halves, which is greater than 1. So it converges absolutely at both endpoints. So my interval of convergence is both endpoints. And then the values of absolute convergence also include both endpoints. So since it converges on the interval and at the endpoints, there are no values of conditional convergence. There are no values where it converges but not absolutely. If it converges, it does converge absolutely. If it doesn't, it doesn't. Okay? So if that makes sense, I hope that helps. And again, if I went a little bit faster, you can always go back, pause, and take a look at it. Think about it, make sure you thoroughly understand what's going on.